So welcome everyone. We'll start this morning with a talk by Patrick Massot, and he will not only explain some lean to us, but actually for some of you maybe also some new mathematics, because he will be talking about filters. Go ahead, Patrick.
Yeah, can you see my screen?
Yes.
Yep. Yeah. So on the schedule of the on the website, on the schedule, you can click this topology link if you want to get my slides, so that you can go back in the slides while I'm talking. So indeed, Johan is right to say that unexpectedly, maybe today you'll learn some mathematics. And the reason for that is the following. You start with limits, which are of course very important in topology, and there are a bunch of them. You've got limits of sequences, and limits of a function at a point, and maybe limit of a function at a point from the right, and maybe you want to record the fact that it goes to y0 but staying below y0, and maybe you want a pointed limit where the x is not allowed to be x0. And of course, there are also infinite limits, maybe at the target or maybe at the source and target and so on. So even if we forget about sequences and say just stick to function from R to R, so the source and target, they could be plus or minus infinity, a point from the left and right, and add on top of those point possibilities asking that x is not x0, and maybe also x is constrained to be in a dense subset, rational numbers. And so what we have actually is not one definition of a limit in this case. We've got 13 times 13 definitions, so that's 169 definitions of limits only for function from real number to real numbers. And that's fine in the real world, because you can just say, I'll give details of one, or maybe 3 definitions among those 169, and the reader figures out the rest. And then you've got lemmas. For instance, limits compose. If f goes to y0 when x goes to x0, and g goes to z0 when y goes to y0, then the compose, g compose f, goes to z0 when x goes to x0. But of course, now we've got 3 places, so 2 source of limits and the final destination. So what we are actually looking at is not one lemma. We are looking at more than 2,000 lemmas. Okay? And again, in the real world, it's not a big deal. You can just prove maybe 3 among 2,000 and just let imagination of people do the rest. Okay, so is it clear what is the problem we have? You can interrupt me if you want. Now, something a bit unusual about this meeting is because every participant is a self-declared curious mathematician, curious about lean, we haven't discussed motivation for doing all that. And there are pretty clear motivation coming from like checking stuff, either because you're tired of the refereeing job, or maybe you would like to make sure your own work is correct. We've discussed a bit about teaching. So Kevin is using a bit lean for teaching. I've been using lean quite a lot for teaching myself. But another motivation is, wouldn't it be great if this kind of question, the fact that in a proof assistant, we cannot simply pretend we've proven 2,000 lemmas when we actually have proved only a couple of them. What if this was the opportunity to invent new mathematics and just come up with the right notion that would fix this issue? And this is not science fiction, because it already happened. This problem was fixed by formalization effort. But it was not fixed using computers, because formalization didn't start with computers. I mean, maybe you can say formalization started with Euclid or people like that. And suddenly people like Cauchy and Weierstrass were also working in this direction. But really the systematic formalization effort for the greater good was really Bourbaki. And Bourbaki basically fixed this issue. They solved this issue. And so this is what we need to learn if you want to use topology in math, just how Bourbaki fixed this problem. So they fixed it with the definition of a filter. So a filter on X, on a type X, is a collection of sets of elements of X. So if you're thinking in terms of set theory, X is a set and it's a collection of subsets, such that the whole thing X belongs to the filter. And if something is in the filter, then anything bigger is in the filter. And the filter is stable by intersection. If U and V, oh, there is a typo here again, sorry. So if U is in F and V is in F, so this is not a subset, this is belongs to F, then the intersection belongs to F. This is copy-paste from the previous line. For instance, the neighborhood filter in a topological space. So if you've got X, a point in a topological space, the set of neighborhoods of X is a filter on the topological space. But you also have the filter at infinity of R. So every set of real number which contains a half infinite interval towards plus infinity is a neighborhood of plus infinity in R. So this is called at top in MathLib. And you can do the same in a natural number if you're interested in limits of sequences. And if you've got, even if X has no structure at all, so the first example used the topology on your ambient type. The next two examples use the order relation. If you have no structure at all on X, you can still enjoy some filters. If you've got any set of elements of X, then the principal filter generated by A, P of A, is simply all sets containing A. Is this definition clear? Do we have questions on the chat maybe? Is anyone here?
No, so there are no questions in the chat so far.
So actually,
all very clear.
This is not quite the definition that Bourbaki wrote in the book, General Topology. Bourbaki added one more condition. They added the condition that the empty set is not part of the filter. So, or equivalently, they added the condition that the filter is not made of all sets of elements of X. And this was a bad decision. And this is another interesting point about formalization in the 50s versus formalization in the 21st century, is that refactoring is much cheaper for us. So I think if you want to modify something in a book of the Element Mathématique of Bourbaki, it's really a lot of work to make sure everything stays consistent. And there have been new editions of Bourbaki books, but not very often. And in our case, we can just change the definition and just let's see where Lean complains, what are the lemmas whose proof need to be adjusted, or maybe the statements. And it's much cheaper to, so this refactoring word, which comes from software engineering, is actually an important one. We can just change stuff and fix whatever breaks, and we are sure that consistency is preserved. So limits. So Bourbaki says, given a filter F on a set X and a point Y in a topological space, capital Y, we say that a function from X to Y converges to small y along the filter F if for every neighborhood of Y, the inverse image of this neighborhood belongs to F. So this is the definition that you found in Bourbaki. But strangely enough, this definition is not general enough. I mean, we need more. And so there is no reason to consider only neighborhood filter at the target. So we say that a function converges to any filter G on capital Y along the filter F on capital X if for every member of the target filter, the inverse image is in the source filter. Okay? And this definition completely solves the problem that we had on the first slide. So now all the limits of the first slide are just instances of this general definition using the examples of filters that we had before. So this is a problem that is completely solved. And it's not only about writing a concise definition and merging 2,000 lemmas into one. The proofs are also nicer. So let's go back to this composition. So first you need to notice that these filters have quite a lot of structure. So first there is an order relation, which is simply a reversed inclusion. So f is less than g if every member of g is a member of f. And we have a push-forward filter, which is defined in the obvious way. And using those two structures, you can reformulate the definition of limit. So f converges to capital G along capital F if f push forward capital F is less than capital G. And very easy verification. So of course the push forward is functorial the way you expect it. And it's each f lower star is order preserving. And so now let's prove that limits compose. So the assumption is that f push forward capital F is less than capital G, and G push forward capital G is less than capital H. And then this is the proof. I mean, on the first line, you use the functoriality composition of push forward. Going to the second line is by monotonicity of G lower star and the fact that the assumption on F. And then the last line is the assumption on G. And that's the proof. And that's the proof that is in Mathlib, just 3 lines computation. And this is proving the 2000 lemmas and many more from the slide 1. Other questions up to now?
So there's 169 definitions that you mentioned of converging. Yeah. How are they, it's not clear to me how they're encapsulated by the notion of filter. What's the connection?
Because we had examples of filters. So for instance, we had examples of neighborhood of X, and so this takes care of X goes to X. But we also have, I mean, I will give more examples of constructions of filters, but this notion of limit when X goes to X0 from the right is also described by a filter.
Oh, I see, right, okay.
Every of those, both the source and the target, so simply converging to Y0 or converging to Y0 from the left or converging to plus infinity, they all correspond to their own filters. So you do need to define 13 filters, but you don't need to have this 13 times 13 definitions. Okay?
Yeah, thanks.
So what else can we do? So no, maybe a bit of summary of what we gained. So this was 100% mathematics, no computer science involved. I didn't even show a lean up to now, and this doesn't exist in the real world. So Bourbaki had a huge impact on mathematics. Most of it is actually hidden. I mean, what Bourbaki managed to teach mathematicians is now so well ingrained in it's so much part of mathematics that we don't realize where it comes from. But that particular thing, the definition of filter and limits using filter, it just didn't stick. So you don't know about it unless you learn mathematics precisely at the right time where Bourbaki had the power to make people teaching this. But this is everywhere in proof assistant. This is not only about Mathlib. I mean, if you go to Coq and if you go to Isabelle, they have filters everywhere. There is no better way to solve this problem.
Patrick, I think in non-Archimedean geometry, we also use filters.
I'm really talking about the general mathematicians. Of course, there are pieces of mathematics where you can't avoid filters, but filters has the general language of limits, and limits, I mean limits in the topology and analysis sense, not the category theoretic limits. I claim this is not the common language of limits among mathematicians today. At least not the mathematicians that I know. And so, and there is no going back. I mean, this is kind of a running joke in our community that every mathematician who comes and see, I'm curious about Lean and I want to do topology, they start by complaining about filters and they say, I want my epsilon and delta back, and what is all this filter craziness? And then after a couple of months, those people who were complaining, they just explain to the next people that they should forget about epsilons and delta and love filters. So let's do more of them. Filters are not only useful for talking about limits, they also allow you to have a unified framework for things like, for n large enough, this property of n holds, or for x close enough to y, this property p of x holds, or in Mother theory, for almost every x, p of x holds. And all those examples and many more, they all mean that the set of x such that the property holds belongs to some filter f. And in Mathlib, and I think it comes from Isabelle, from another proof assistant, we have a notation for this, which I don't think exists in the real world. We write for all exponent f is for filter, for all x in this filter capital F, p of x holds. So this is also very convenient, and the properties of in the definition of a filter, they translate very nicely to properties of this notation. And let's take an example. Say we have a topological space Y, and X has some non-trivial filter, so a filter which does not contain every set of elements of X. If you assume that for all X in this filter, the function phi of X belongs to V, and phi converges to Y along this filter F, then Y is in the closure of V. You see? So for instance, in the elementary situation, maybe that could be if I have a sequence of points of V and it converges to Y, then Y is in the closure of V. But you already know that in this statement, asking that all elements of the sequence belong to V is too much. You only need to know that for n large enough, the elements of the sequence belong to V, and then the limit belongs to the closure of V. Okay, so this is also a nice use of filters that is was introduced comparatively recently in Mathlib, but it's just put in more and more places in the mathematical library in Mathlib. Now what next? I don't remember. Pulling back filters. I announced more structure. So we pushed filters forward already, but we can also pull them back, of course. So the definition is not very difficult. It's slightly more complicated than push forward, but the examples are more important. So for instance, if we have a subspace, so X is a subspace of Y, and I've got a function defined on X only, and a point Y0 in capital Y, then you can ask things like limit of f of x when x goes to y0 but staying in capital X is z0, and this is expressed in terms of the pullback of the neighborhood filter. So I upper star of the neighborhoods of y0 is the neighborhood filter pulled back to the subset. Okay, so this is probably the most natural example of a filter pullback. And of course, the pullback is a contravariant and monotone, and push forward and pullback form a Galois connection. So this is what you learned from Kevin yesterday. This is the word, I don't know where this, who really uses this word Galois connection except in proof assistant, but it simply means that you've got this adjunction. So F push forward is less than something if you are less than F pullback. Okay? And there is a complete lattice structure. So I'm writing a few definitions. So you've, again, from Kevin's talk yesterday, you've learned how to love lattices. And I just explained how to take the union or the join of two filters, or the maximum of F and G. So this is pretty easy. U is in F sup G if in both, and the join, so the minimum operation or the inf operation is just a set is in the inf of F of G if there are elements of F and elements of G whose intersection is contained in U. And I haven't written the definition for general inf and sup for not only two filters, but arbitrary families of filters, but they are also there. And this is a complete lattice. So you can do sup and inf of arbitrary families, and there is a bottom element, which is characterized by the fact that every set is in the bottom filter. So this is the trivial filter that Bourbaki didn't want to see in the book. And the top filter is much less important. The top filter contains only the whole ambient type. And you see the fact that we allow this bottom filter is, I mean, it gives us the lattice structure. If you don't allow this bottom filter, then this operation, the inf, is not always well defined, and the pullback is also not always well defined if you don't allow this bottom filter, this trivial filter. So this is all part of this philosophy that it's much better to hit first and then negotiate. I mean, you really want to be able to write inf and write a pullback filter. And then if you need that the result is not the trivial filter, is not bottom, then you put that in assumptions of some lemmas like we had before in the lemma, in this last lemma about belonging to the closure. We need this assumption that f is non-trivial. So you just put the assumption in the lemma, but not in the definition. Okay, and I think, I missed one piece. So often it's convenient when you have a concrete filter, when you're not doing the abstract theory of filters on a type, it's convenient to talk about bases of filters. So if you have a families of set of elements of type X and a filter on X, you say that this family is a basis for your filter if belonging to the filter is the same as containing an element of the basis. And this is a very common situation. Actually, in the examples that I gave, all the filter examples, the concrete filter examples that I gave, they have natural bases. If we go back to slide 1, almost, yeah, the neighborhoods of X, they have a basis which is the basis of open neighborhoods. Or if you are in a metric space, you can even talk about the basis of open balls centered at X. And those two filters, they are explicitly defined in terms of containing something. So clearly, we also have a basis here and here. And here the basis is simply containing A itself, or the principal filter. And how it's formalized in Mathlib is this predicate. So for technical reason, it's defined as a structure with only one field, which looks a bit silly, but when you start adding condition on the basis, it's convenient to be able to extend this by putting more field. And so you start with a filter on X, and also it's convenient to have not only an indexing type iota and this function B, but also a predicate on iota, so that really the elements of the basis are only the Bi when I satisfies P. So the condition is for all U, oh, this is a typo, U is in L, if and only if there exists I such that Pi holds and Bi is contained in U. Okay, so this is the notion of having a basis. And when you have a basis, you can check things like limits or inequalities and stuff like that by caring only about the basis. So for instance, if F has basis S and G has basis T, then checking that small f converges to capital G along capital F is the same thing as checking that for all j there exists I such that Si is in the inverse image of Tj. So for instance, you know, if you want to check that a function between metric spaces is continuous, you don't really, at some point x, you don't really need to check that for every open set containing x, the pre-image under the function is open. You only need to check that the pre-image of an open ball around x is open, and for this, it suffices to prove that it contains an open ball around X. So I messed up the X and f of X, but you fixed it. Okay, you see what I mean? An open ball around f of X, the pre-image under F should contain an open ball around X. Hopefully that one I got it right. Okay, and so we're almost ready to go and make some exercises, but I think I've got one slide. Yeah, I've got a couple more slides because one of the exercises, maybe we can first have a look at the exercises. So the exercises are in the usual place. So in Friday topology.lean. And the first exercises are just getting used to the definition of filters, redefining the principal filter. So this is in namespace LftCM. Maybe I should put this bigger so that you. So you just check that the principal filter. So yeah, it's in namespace, so it won't clash with the mathlib principal filter. So just check that the principal filter is indeed a filter. At top is this filter on N, or actually you could use any pre-ordered space here, and just being slightly more careful if your pre-order is a bit nasty, but so you can check this also, and I've put the construction of a neighborhood filter in case of a real number. I wrote it slightly more tricky because you need to know a bit more about how to handle intervals and arithmetic in R, but of course conceptually there is nothing tricky at all. And some comments on how the lemmas are accessible. You can read all that. And the exercise about the definition of tends to. So your first I tell you how you could do this composition of limit by just using elements of the filter, not getting functorial. And then there is the nice 3-line computation proof that you can also enjoy doing. An exercise about pullback. So pullback is comap and push forward is map. So those names were chosen by people having a different background and people who will not say push forward and pull back. They are defined by people who like monads in computer science. And small exercise on properties holding eventually. So this is this for all in the sense of filter X in a filter PX, just a small exercise. And then we come to continuous map. There are comments about closed and open and compact subsets of a topological space, how they are handled in mathlib, and proving a couple of stuff. But then the big exercise is proving extension. So proving this statement here. If you've got a subset A of a topological space X, and A is a dense subset, and you have a continuous function on A, and you want to extend it to a function on the wall X. And you assume, in order for this extension to exist and to be unique, that for all X, there exists Y such that F tends to Y along the pullback of the neighborhood filter of X. So this is, remember, this is really saying that f of X tends to Y when, so f of X prime tends to Y when X prime goes to X while staying inside A. Then there exists a continuous map phi, so that phi compose, I would iota of element I is F. So this is the basic theorem about extension by continuity, and the exercise is, so there is an auxiliary exercise first, and then the exercise is to prove this extension theorem. And there is a proof here in the comments, but I also have I've written the proof in tech, and so we'll have a poll to determine whether I'll go through this proof in 1 minute. But let me mention that the last exercise is about metric spaces in Lean, And so this is a Heine contour for metric spaces. So if you've got a compact metric space, any continuous function on this compact metric space is uniformly continuous. So if you don't like general topology and you just want to skip to metric spaces, you can instead read the explanation here and try to do this proof. And let me mention that for reason of time constraints, I'm skipping over uniform spaces, but really everything in MathLib that holds more generally than for metric spaces, but not quite for every topological space is done by uniform spaces, which is also, I think, due to Bourbaki, but we won't have time today to discuss uniform spaces. So maybe, no, you need to tell me, do you want me to explain the proof of this theorem, or do you want to read the proof on my slides that are on the website, or maybe read the proof in the lean file, which is of course a bit harder to read despite Unicode? What should I do? Because I've already talked for half an hour, which is kind of the upper limit that we fixed.
I mean, personally, I don't want to read your proof. I just want to figure out what the proof is on my own.
Okay, that's good.
And maybe we can start the exercises and people can just, I mean, we could leave you in the main room and then you can pop into breakout rooms if people need help.
Yeah, yeah. I think, I mean, my opinion is that we should go to the exercise session, but if people want to listen
so let's do that.
to this proof,